Okay, the second example here is we want to compute the surface integral where the function is x ds over the surface sigma, and the information provided about the surface is part of the y equal to x squared plus 4z, and they give you the limit of the x and the z. So I don't think you can see this particular example in the exam, okay, but it's okay because you're just learning for this subtopic, so that's why they give you the limit. So the limit of x 0 to, and the limit of z 0 to as well. So why they give you the y only x and z? Because if you have this function, this equation in this form, so we know that the surface function is in the function of x and z. So your region is on exact plane. So you don't need to sketch for this example. You don't need to sketch because they are all given. Okay, so now you have to find the ds in terms of dA. So the formula that you have to apply here is you have to find fx squared plus fy squared plus fz squared. This one I put in general, but since now it is y, right? So yx squared plus yy is 1 plus yz squared dA. So you have to differentiate y with respect to x will give you 2x, right? So you have 2x squared plus 1, and y with respect to z will give you 4 squared. And you will have this. Then this maybe simplify, then we have 4x squared plus 17 square root of dA. Okay. So now your double integral, your surface integrals become x square root 4x squared plus 70 dA. And then we use r over the exact plane. And since the limit are given for x and z, when we can use them directly, and since they are all constant, you can put you can choose any order of integration that you want to. So let's say I want to solve for z first, z dx. Okay, and what is the limit of z? 0 to, and x also 0 to. Okay, so now we can start to, now from the surface integral ds, now it's convert into dA. Then when you substitute, then here you have the standard form of the double integral in terms of dA. So now the way you want to compute the double integral is exactly the same as in chapter 3 for double integral. So now we solve for finding the integrate respect to z first. So you have 4x squared plus 17, and then z. We give you constant 0 to 2. Yes. Then it looks like you have the 2, then x square root 4x squared plus 17 dx. Okay, so before we proceed to calculate about the function here. So now look at the integrand. So your integrand is x. So since you decided to have this particular function where y is a function of x, so the possible variable that can be put as the integrand here, because it is x, right? Only x and z, no y. So if you look at, you check your integrand here, it is already in terms of x. and also z, so no y, so then we can proceed. Otherwise you have to replace the y. Okay, so hopefully you're clear with that. Otherwise you will get stuck. Okay, so now we integrate this using the substitution. Okay, so when you use the substitution technique, so here we let u equal to 4x squared plus 17. So d over dx is 8x. Then dx is equal to du over 8x. Okay, and when you replace that x, and you have u half, and dx is du over 8x. X here can be cancelled out. You have 1 over 4 u half du. So now your form is more simpler after you apply the substitution into u. So then we integrate respect to u 3 over 2, 2 over 3. So you have to replace the limit of x is 0 to, so 1 over 6, and u just now is given by 4x squared plus 17 to the power of 3 over 2, 0 to 2. So be careful when you replace that. Easy for you to get a mistake. So 1 over 6 and replace 2. 2 to 4 for 16 plus 17. 3 over 2 minus 17. 3 over 2. So 1 over 6, 33, 3 over 2 minus 17, 3 over 2. Okay. Okay, you can leave your answer in this form. So I'm sure that the answer will be the same as this. Okay, so that is for the second example. So look at the remark here. The greater challenge here is to evaluate the outer integral. Thus, knowledge of the basic integration formula is essential. Okay, so meaning that your knowledge about the double integral that you have learned in chapter 3 is very, very important. And also the way you want to choose the method of integration is also crucial here. Okay, the third example, we have to evaluate surface integral of y square z square ds over the surface sigma part of the cone that lies between the z equal to 1 and also z equal to 2. Okay, so remember this one is not a solid. Okay, we are talking about the surface integral. So for this example, it is not solid. If you have solid, then they will say it. But in this case, it is open surface, where your cone is just in the some particular size where it is bounded by the z1 and z2. Okay, but it is not closed. If it is closed, then we will say that it's a solid. So when you sketch that, then your cone is so that let's say that one is this is z, x and y. So this one is equal to 2 and this one is equal to 1. So meaning that I have to erase the curve for the surface which are not part of the surface that we are discussing here. Okay, so that is your surface. So your surface is part of the cone, which is lies between 1 and Z1 and Z2. Okay, so now we want to evaluate this surface integral. Okay, so here you need to find the ds. So your function here, so your function here is in terms of xy. So here the ds is square root of zx square plus zy square plus 1 d. So differentiate. Okay, so your z here is x squared plus y squared to the power of 1 over 2, which is square root, right? And then when you differentiate z with respect to x, this will give you 1 over 2 x squared plus y squared negative 1 over 2. You need to apply the chain rule and differentiate the inner function with respect to x. So this will give you 2x plus 0. 2x. Then when you simplify the 2 gone, so you will have x over square root of x squared plus y squared. So we have when you square that, you will get x squared over x squared plus y squared plus, and similarly for zy, you have to differentiate the outer, which is the same as zx, and then multiplied by the derivative of the inner function with respect to y. So you got 0 plus 2y. 2 cancel out. So you will have y over square root of x squared plus y squared. And when you square that term, then will give you y squared over x squared plus y squared plus 1 dA. So dA should be outside the square root, alright? So don't be confused. So when you get this, can we simplify this form, these two forms? So you have the same denominator. It seems like you can just directly adding them together, right? So then you have x squared plus y squared over x squared plus y squared. So you can have x squared plus y squared over x squared plus y squared plus 1. Don't forget the square root and dA. So this one will give you 1, right? 1. So you have square root 2 dA. So that is your ds. So then we substitute your ds into your original surface integral, then you will get y square z square, then now your ds is square root 2 dA over the region, and your region is on xy plane. Okay, so now your double integral, your surface integral is reduced to the standard double integral. But before you proceed to calculate the double integral, you have to look at your integrand. Okay, so ask yourself, what is the possible variable that can be allowed here in this expression, especially for the integrand here? You should only have x and y, right? But you have the z here, meaning that you have to replace the z here in terms of x and y. How can you get that? So finding the z, how can we get that? So you look at your function for the surface. So z is given by, so from here you have this one. So meaning that when you want to replace the z square, so you have to find the z square. So meaning that your z square here is equal to x square plus y square. So you have to substitute your double integral now becomes, So y squared is okay, but the z squared is x squared plus y squared dA, square root dA over the region R. So then we explain. So you have x squared plus y squared plus y4, and you can take out the square root to dA. So now we have a standard double integral, and now dA, you have to look at your region. Okay, now ask yourself, since you have this particular equation, so you can say that your region lying on xy plane. So what can you see on the xy plane? Remember last time in chapter 3, and I mean in the double, when you compute the double and triple integral, especially this one double integral, we have to find the region, right? So what is the region? The region is something that when you know that your region is lying on xy plane, meaning that what you can see when you're standing along the z up there. So what can you see when you are looking down? So the shape that you can see is there are two circles, right? The circles when you have z equal to 1, and the second one when z is equal to 2. So your region is lying between these two circles. But what is the radius of these two circles? So by looking at your function z, your coordinate equation, so z equal to square root of x squared plus y squared. So when z is equal to 1, so what is the shape that you have? Is it really a circle, or can be an ellipse, or can be any other curve? So we have to replace the z equal to 1 into the equation of the sigma. So you have z equal to 1 equal to x squared plus y squared. Then you can have x squared plus y squared is equal to 1. So meaning that when z is equal to 1, your circle, you have a circle with this one. Okay, so that is z equal to 1. And then how about when z is equal to 2? So you replace 2 equal to square root x squared plus y squared. Then this will give you a circle with radius 2. So you have 2 here. 2, 1 on y-axis plane. Since your region here is a circle, a circular region, so I don't think I want to proceed the calculation here using Cartesian, because it can be solved, but it's quite tedious. So I want to solve this using polar. Okay, so using polar, so this one is actually r square, isn't it? Yeah. So then I just replace the y squared. So r sine theta square, r square, then dA is r dr d theta. Right. Okay, so now determine the limit of theta. Look at your region. They don't mention about the first octant, right? So meaning that it can be all over the quadrant here. So your theta is from 0 to 2 pi, a complete circle. So 0 to 2 pi. Okay, now about the limit of r. Look at your region again. And how can we determine the limit of r? Remember that? You have to draw a line starting at the origin here and passing through all the possible region. So you can see that the lower bound of r for all over the quadrant, they are all the same, where r is from not 0, right? When r is 0, meaning that there is something, your region, your shaded region should be also passing through the origin, but now it is empty here, so it starts from the r equal to 1, and then ending at the largest circle is at 2. So your r is from 1 to 2. So R from 1 to 2. Okay, now that's time for us to evaluate them. I have to simplify first. So R4, R5, R5 sine square theta dr d theta 0 to pi 1 2. Okay, so when we simplify, so first integrate with respect to r, so we've got rc over 6. I replace the limit and we got this, and then now we integrate the sine squared, so we cannot directly put the sine cube over 3. You have to reduce the power of square, the power here, by using the identity of 3 go. And then we use the 1 minus cos 2 theta over 2. So this one, you can check the list of formula provided. So it is given. Then you can integrate with respect to theta. So you got 2 here, I bring it out. It become 12. So now I have theta minus sine 2 theta over 2. Okay, so this one I bring it up. So you got 12 here. And then we can substitute the limit. And finally, so this is the answer. Okay, so that is for the example 5.13b.